This seminar presents an example of water-cooled plate heat dissipation in a conduction-cooled power supply. Firstly, let's look at conduction heat dissipation using water-cooled plates. Conduction heat dissipation using a water cooling plate is a method of dissipating heat generated by a power supply through a water cooling plate. Cooling water is circulated through the water cooling plate to dissipate heat. The cooling water that absorbs the heat from the power supply is cooled in a heat exchanger and used again to cool the power supply. Power supplies that are capable of conduction heat dissipation are those that have a plate for heat dissipation. The advantages are the ability to handle high power and its quiet design. But it must be noted that the heat dissipation capacity depends on the temperature and flow rate of the cooling water. Next, let's discuss water-cooled plate heat dissipation in conduction-cooled power supplies. First, let's look at the HCA 3500TF, a conduction-cooled power supply that is designed for water cooling. The HCA 3500TF is a conduction-cooled power supply designed for water cooling, with an output power of 3,500 watt and two output voltages to choose from, 48 volt and 65 volt. Wide input range of 3-phase 200 volt to 400 volt is available to meet the power supply requirements of various countries around the world. High efficiency and conduction cooling with water cooling enables maximum power output at ambient temperatures up to 70 degrees Celsius. Here, I will showcase an example of heat dissipation design using water-cooled plates in the HCA series. The design conditions are as shown. To use the power supply under these conditions, we will find what temperature per watt the thermal resistance of the water-cooled plate needs to be under. First of all, I will explain the flow of heat radiation. Heat generated inside the power supply is dissipated into circulating water that goes through the baseplate, thermal interface material, and water-cooled plate. This is what it looks like when represented as a thermal network model. In this model, internal losses are replaced by current sources. The voltage generated by passing the hypothetical current through the thermal resistance present in each heat dissipation path can be expressed as a temperature difference. After this, the process is divided into 3 steps to find out under what temperature per watt the water-cooled plate needs to be. Step 1. Calculating the internal loss PD of the power supply. Calculate output power from the output voltage and load current to be used. Next, read the efficiency at the load current to be used from the efficiency and load properties in the power supply's property data. From this efficiency/load properties, calculate the internal loss using an efficiency of 94.7% at 400 volt input voltage and 50 ampere load current. Step 2. Calculating thermal resistance datum of the thermal interface materials. Even with heat dissipation using water-cooled plates, contact thermal resistance must be reduced, and thermal interface materials are required. A heat dissipating sheet is used in this example, and the contact thermal resistance is postulated to be a pore 3. Now we will calculate the thermal resistance status of the contact surface. The thermal resistance of a contact surface, contact thermal resistance, is obtained by dividing the thermal resistance per unit area by the contact area. Next, we need to find the thermal resistance datum of the thermal interface material. Thermal resistance can be calculated from the contact area, thickness of the thermal interface material, and thermal conductivity, which gives us the thermal resistance as shown. Step 3. Calculating thermal resistance theta W of water-cooled plates. First, read the upper temperature limit of the power supply baseplate from the specifications. From the output power/output voltage, the baseplate upper temperature limit can be read as 55 degrees Celsius. Then determine the target upper water temperature limit. The overall thermal resistance is then calculated from the internal losses found in Step 1 and the temperature difference between the baseplate upper limit temperature and the water temperature. The thermal resistance required for the water-cooled plate can be obtained by subtracting the thermal resistance of each part calculated earlier from the overall thermal resistance. Now let's postulate a water-cooled plate property graph like this one. Since the thermal resistance of the water-cooled plate depends on the flow rate, the assumed flow rate of 2 liters per minute, and the calculated thermal resistance indicate that water-cooled plate B is just usable and water-cooled plate C is well within the limit. This is a summary of examples for the water-cooled plate heat dissipation design. The thermal resistance required for a water-cooled plate can be estimated based on the conditions of use. Thermal interface materials should be placed between the power supply and the water-cooled plate to ensure a tight fit. When determining internal losses, property data should be checked from the technical data on our website. Thank you for watching.